7.3 is modeling data using exponential functions. So we've looked at linear functions, we looked at quadratic functions, now we're looking at exponential functions. So if you remember, exponential functions is when your data is growing by basically an exponent. So it's either increasing or decreasing exponentially. A lot of times we look at, in chemistry, when you're looking at half-lives and so on of different elements and things, that's exponential, either growth or decay. So example 1 says, an insect colony doubles its population every 15 days. The colony begins with 200 insects. Fill in the chart below to show the number of insects after 90 days. So we know that every 15 days we're going to have twice the amount that was there before. So we started at 200. So on the first, after the first 15 days, we're at 400. Another 15 days, we're at 800. Another 15, we're at 16. Then we're at 3,200. Then we're at 6,400. And then by the time we get to 90 days, we will have 12,800 ants, all of which live in my basement. So what we want to do then, in order to figure out what this data will look like, is we create the scatter plot. So nothing different than what we did with the linear and the quadratic. So again, your y data is going on the vertical, and your x data is going on the horizontal. Remember, x is your independent information, and y is your dependent information, or your dependent variable. So the x's, we can put in whatever value we want, but what we end up with the y will depend on how many x's we have. So our x's here are going to be our days. That's the dependent part, because we could pick however many days we want. So if we go up by 5, so every second line will be all number here. Yep. That was a 70 and an 80 together. Okay, and across the y's then, that is our dependent. So depending on how many days we look at will tell us how many ants we have. So we're going to start, instead of starting at 0 and going 100, 200, 300, we're going to start, since our very first our data was going from 200 and then up to 12,800. I'm just going to do this at, I'm going to go up by 1600s every, so I guess 800s, but I'm going to number every 1600. I missed my 8,000, I suppose. So when you're doing your data, you don't have to go up, or when you're doing it on your graph, you don't have to go 100, 200, 300. You can do a jump from where you think your data needs to start, just so that you can fit it onto your graph. So now it's a matter of plotting. So at day 0, we were at 200. So if this is 800 is the first ticky mark, so 200 is going to be pretty close to the starting point. At day 15, we were at 400. So that's halfway up there. Day 30, we were at 800. Day 45, we were at 1600. Day 60, we were at 3200. Day 75, we were at 6400. And I gotta make this match up. And day 90, we were at 12,800. So up here. Okay. So that's what the scatter plot would look like. I'm just gonna put this onto 2 pages here. Oh. Okay, so the B part says use your calculator to do an exponential regression of the data to determine the curve of best fit. Sketch this on your graph. So what you have to do then is you have to go into your stat, do your lists, and then once you've got your list, set your window for your data, and then hit plot or hit graph. Make sure you have stat plot on. Okay, well, I'll just use my data from here. Okay, so I'm going to have to quit. I need to clear these, otherwise it's gonna mess up our... Oh. Okay. So I want to edit because I'm going to put in my data. I need to go up here and clear it. Okay, whoop. All right, so my list one, those are my x variables, so that's going from 0 to 90. Oops, better make that 90. Okay. List 2 then, that was my y values, my ants. Okay, so I've got my data in there. For my window then, you could go just to 0, you could go to -10. I'm going to leave this one at -10. For my window though, to go the other way, I'm going to say 120, go a little bit past what we need. My x scale, I want to go up by 10s. My y minimum, -2 is fine, that's just showing me a little bit there. My y minimum, I'm going to put my 1600 in. My y maximum, just because of a question we have coming up here where it's at the 20,000, I'm going to go to 32,000, or 32, not, yeah, 20,000, 32,000. My y scale then, I'm going to go up by 800s. Alright, so now we should make sure our stat plot is turned on. No, mine's off, so make sure that's on. We want on scatter plot. Okay, so now we're going to graph this. So I'm going to have to, I'm going to change my window a bit so I can see a little bit further down. So my window here, oh, y minimum. So maybe we'll do that at, well, I guess I have to go, yeah, I need to go at least 200. Let's go 0, I guess. Okay, there we go. Now we can at least see that. Okay, so you have your graph, which looks similar to the graph that we have there. So then it says use your calculator to do an exponential regression of the data to determine the curve of best fit. So exponential regression, we go back into our statistics. We want to calculate. Exponential regression is down. There's linear, quadratic. And there's exponential regression. So I guess it's 0 on the... Okay, so we want list 1 is our x list. List 2 is our y list. Calculate, enter. So we have y is equal to a times b to the power of x. I'm just going to write this above because I think you have more space on yours than I do on mine. So ab to the power of x is our exponential function. So it said a was 200 and it said our B was, and I'm going to round this to 1.0, well, I'll put 1.047 just on here, but when I'm doing it into my calculator, I'm going to put the full decimal. Actually, I'll write it all down. 294,123 to the power of x. And the reason why I'm doing that is when I put this in and do my calculations for D and E, it makes a difference when you've rounded it to, when I did it the first time, I only did it to the 3 decimal places, and it gave me a slightly different answer than if I put in the whole value in there. So that's our curve. So now it says sketch this on the graph above. So if we put it back into our calculator, do our y equals, so it's 200 times 1.047294123 close bracket to the power of x. Well, I wonder if that's gonna. There we go. I don't know why I had an extra spot in there. Okay. So now when I do my graph, that's what it looks like. Okay. So basically the graph is just going through those points. And it would continue on. Whoops, pretend that one went through that point there. Okay, so C part says, explain how the values of A and B you calculated model an exponential growth function. So with our formula, if you want to call it, the y is equal to A times B to the power of x, our A is always, no matter what we're looking at, it's always your starting point. So, or in this case, our starting population. And it says, how do we know that this is exponential growth function? Well, we know it's a growth because our b value is greater than 1. If our b value was a fraction or a decimal value less than 1, then we know it's going to be a decay. So the exponential function models growth because b is greater than 1. So if b had been a fraction less than 1, or a decimal less than 1, or any value less than 1, then it would be a decay. So it says use your calculator to determine the insect population at 65 days. So we could look off our graph, but remember, just even from my drawing on this graph here, I'm a little bit off. But if I just take a look at the graph, this one wants us to use the calculator, but on your graph, it's basically just a lineup, right? So I don't know why it keeps moving this over, but it's basically there. So it should be about 32, so about 4,000-ish. If we do the calculator, it's more accurate and it's super easy. So what you need to do is you go into your stat. I'll just write the stats here. So I do stat. Oh. So I do stat, I want to do calculate. Oh, no, I did the wrong one, sorry. Not the stat, calculate. Forget that. I just want calculate. Just calculate, so second trace. I do calculate, and I want value. I want to find out what is my value at an amount. So value, I hit enter, x equals. Whenever you do the value, it's saying, okay, you give the calculator the x value, and it'll tell you what the y value will be. So then I do my 65, so x equals 65, hit enter, and it tells you. So that's where it would be on the calculator. So then you can have a look, or then you can find your value without even doing any calculation. So your other option too would have been just to put in a 65 into that x and do it on your calculator that way. This way is quicker and more accurate. So in this one then, when x equals 65, y is equal to 4,000 and basically 32. So there's 4,032 insects at day 5, or day 65. So now it says use your calculator to determine the number of days until the insect population reaches 20,000. So I could look off of here and see if I can get my y to 20,000. So this is 14,400. Another, what am I going to add on there? Another 1,600 isn't going to get me to 20,000. So on my graph, it's hard to figure that out. I could try to do a trace on the graph itself here. So I can move along here until whoops, go back on the graph. I could do it this way until I hit y is equal to 20,000. Okay, I'm too high there. But you can see it's hard to get it at exactly 20,000. So doing it this way works, but it's not as accurate. So it tells me it's at about 99.3. The other way to do this is, again, to use the calculator, but do a y equals. So let's say y equals 20,000, which is what we want. So put y equals 20,000, and then graph. One, two, three, four, 5. Graph it. There's the line. So I can see from there, that doesn't give me the value. So now if I do my second calculate, I want to do the intersect. Okay, so this is calc, intersect. I want to know where those two lines intersect. So it doesn't matter that my first curve is on the half of a parabola, or that function, so I can hit enter. Second one is on that y is equal to 20,000. Enter, do my guess, and it tells me 99.657. So at 99.657, so almost the 100th day. Okay, so if you're doing a question where it's asking you to find what the x value would be given the y value, so what the dependent value would be given the independent, or sorry, the other way around, what the independent value is given the dependent, put the dependent value into an equation, and then just do your intersect calculation and you'll get the right answer. So in the need to know here, the exponential regression model is fx is equal to a times b to the power of x, where a represents the initial value, so that's what you're starting at on day 0 or hour 0, minute 0, whatever the 0 value is, and b represents the growth factor if b is greater than 1, or the decay factor if it's between 0 and 1, so if it's a decimal. You can't have a negative value for the b, otherwise, well, it just won't work. An exponential curve of best fit can be used to predict values that are not recorded or plotted. Predictions can be made by reading the values from the curve of best fit on a scatter plot, or by using the equation of the exponential regression function. So that's what we did here. We tried to do the reading, and it worked fairly accurately, but it depends how good you are at plotting your points and how accurate those are, whereas using the calculator will give you a more exact value. So there's your assignment. Have fun.